So in this video, we conclude our chapter on the spectrum of operators acting between Banach spaces with a formidable theorem called the Fredholm Alternative. This is a theorem for compact operator on any Banach space, and what the theorem tells you is that if you look at the operator lambda identity minus t for any non-zero lambda, this operator is what we call a Fredholm operator, meaning that the null space is finite dimensional, the range is closed, and the range has finite codimension. Now, from this theorem, we will derive a range of very nice spectral consequences, at least in separable Banach spaces, for our compact operator. We'll have corollary 13.4 that tells us that being a bijection is equivalent to being injective, is equivalent to being surjective for a map like lambda identity minus t in that context. We'll have corollary 13.5, which will be the analog of what we had in Hilbert spaces, that the spectrum away from the origin has to be finite. And last but not least, we'll get corollary 13.6, a big part of what formed the proof of the spectral theorem in Hilbert spaces, namely the fact that spectrum of compact operators away from zero can only be made of eigenvalues, and this eigenvalue, this set of eigenvalue, is either finite, or if it's a sequence, that's a sequence that tends to zero. So we will prove all of that, lifting our results from Hilbert space theory back in chapter 3 to at least separable Banach spaces in this chapter. And the key thing to do first is to prove theorem 13.3. Now, before I do so, I can't resist just hinting at the fact that this theorem is not just a way to get this nice spectral theory for our course. It is also the starting point of what's called Fredholm theory that studies the index of operator. That is to say, the number that you get from subtracting the codimension of the range from the dimension of the null space. Now, that number carries a lot of information. It carries information about solution of certain partial differential equation if you take a compact operator t that arises from these equations, like we've seen before when we've looked at solving a PDE and getting a solution map that is compact between Hilbert spaces or even between LP spaces, thanks to Sobolev embedding theorems. So for this type of operators that arise from PDE, the index of the operator carries PDE theoretic information. But the most beautiful theorem about index is due to Atiyah and Zinger. This is a Fields medal winning theorem that tells you that this analytical index of a compact operator, or more precisely an operator of the form lambda identity minus a compact, is equal to the topological index. So when the operators do arise from differential operators on certain manifolds, then computing the index gives you topological information about the manifold. But we won't go down that path. We will just prove the starting point of this entire theory, which is the Fredholm Alternative theorem. Let's do that now. Okay, so the first thing to notice is that without loss of generality, we can take lambda to be 1. If not, you replace t by t divided by lambda, and that's still a compact operator. Now, the first thing we will show is that the null space of identity minus t has finite dimension. And the way to do that is the following. Well, first of all, you realize that this is a closed subspace of the Banach space X, so it's itself a Banach space for the norm of X. Okay, and now if you take any X in this null space and you assume that the norm of X is smaller than 1, then you have that X is equal to T of X because it's in the null space, and therefore it belongs to the image of the unit ball of capital X by T, because norm of X is smaller than 1, and that's included in its closure. So what have we got? We've got that the unit ball of the null space is closed in T of B of X, which is compact. So this Banach space as a compact unit ball for the norm, and we have seen that this characterizes finite dimensional Banach spaces. Therefore, this is compact, and that's the null space is finite dimensional. Okay, so we've proven that the null space has finite dimension. Our next step is to show that the range is closed. Okay, so to do that, we pick a sequence un in X and an element, let's call it f in X, and we assume that un minus t un tends to f. And now we have to show that f is in the range. So to do that, we're going to do the following. So we're going to define dn to be the distance of un to the null space of I minus t for all n. And then we are going to pick a Vn in the null space such that un minus Vn is almost that distance. So it's smaller than dn plus 1 upon n for all n. Okay, so now there's two possibilities. Either this sequence un minus Vn is bounded or it's not. So let's have a look first at the case where it is bounded, and we'll see that this gives us our conclusion. And then we'll look at the case where it's not bounded, and we'll show that this case is impossible. Okay, so first case, assume un minus Vn is bounded. So that's step 2a, let's say. And if that happens, then I can use compactness. And by compactness, I can extract a converging subsequence from the image of by t of un minus Vn. So there exists a subsequence unj minus Vnj that is such that t unj minus Vnj converges. Okay, let's give a name to the limit. So let's say there exists a g in X such that t unj minus t Vnj tends to g as j goes to infinity. Now remember that my Vnj is in the null space of R minus t, so t Vnj is actually just Vnj. So what have we got? We've got that unj minus Vnj is really the same thing as unj minus t Vnj, and that is the same thing as unj minus t unj plus t of unj minus Vnj. So this has a limit as j goes to infinity, and the limit is f plus g. Okay, so unj minus Vnj tends to f plus g. So what does that tell me about identity minus t of f plus g? Identity minus t of f plus g is going to be the limit as j goes to infinity of identity minus t of unj minus Vnj, but identity minus t of Vnj is 0 because Vnj is in the null space of identity minus t. So this is the same thing as the limit of identity minus t applied to unj, and we know that the limit of that is f. Okay, so we've just proven that f is identity minus t of f plus g, and therefore belongs to the range of identity minus t. So we've proven our result, right? We've proven that when I take the limit of a sequence un minus tun, I get an f which has to be in the range. So this would prove that the range is closed once we've shown that this assumption is always satisfied. So our next step is to assume that un minus Vn is not bounded and derive a contradiction. Okay, so let's see what happens if we assume that un minus Vn is unbounded. We'll see that this cannot happen. Alright, so if un minus Vn is not bounded, I can extract a subsequence that goes to infinity, and I can also use compactness of my operator t. So let's do the following. Let's take a subsequence such that UNK minus VNK tends to infinity. I can do that because the UN minus Vn is not bounded. And in the meantime, if I look at T of UNK minus VNK divided by its norm, okay, I would like this to converge to something. So such that this happens and there exists a y in x such that this tends to y as k goes to infinity, which is possible by compactness of t. And of course, I'm dividing here by something that tends to infinity. So in particular, I can assume it's non-zero for every k. Okay, so I pick a subsequence that does that. And then let's define what we added w and k, say, to be u and k minus v and k divided by u and k minus v and k. Okay, so what can I say? Maybe let's simplify notation, just call that wk. What can I say about this wk? Well, the norm of u and k minus v and k goes to infinity. And the norm of 1 minus t of u and k minus v and k remains finite because 1 minus t u and k has to tend to f. So if I look at 1 minus t wk, I get 1 minus t of u and k divided by the norm of u and k minus v and k, because v and k is in the null space of 1 minus t. And so if I take the norm of that, this has to go to 0 as n goes to infinity, because 1 minus t of u and k tends to f. So k goes to infinity. Okay, so 1 minus t of wk goes to infinity, and t of wk goes to y. And then in the meantime, the distance between wk and the null space of I minus t is equal to what? Well, it's equal to the distance of u and k divided by u and k minus v and k to the null space, right? Because v and k doesn't change anything, it's already in the null space. And then this is equal to dk, by definition of dk, divided by u and k minus v and k. But u and k minus v and k is smaller than dk plus 1 upon k, so dnk. So this entire thing here is certainly greater than dnk divided by dnk plus 1 upon nk. And I don't really care what that is, but one thing for sure is that as k goes to infinity, this goes to 1. Okay, so let us exploit all of these facts and get a contradiction. The idea is that this property here, that you stay away from the null space, looks like it should be incompatible with this property here that says that wk is an approximate eigenvector for the eigenvalue 1. Now let's see how we turn that into an actual contradiction. Well, what happens if I look at 1 minus t of y? Well, 1 minus t of y is really the limit of t of 1 minus t applied to wk as k goes to infinity. But we've just seen that 1 minus t wk goes to 0, so this goes to 0. So this is telling me that this y that we got here as the limit of the t wk belong to the null space of identity minus t. Now that seems implausible, because then that means that 0 is the distance between y and the null space, and that distance is also the limit of the distance between twk and the null space as k goes to infinity. But then if I add and subtract wk, I get that this is the same as the limit of the distance of twk minus wk, which we know goes to 0, plus wk, the distance from that to the null space. And now this is the same thing as the limit as k goes to infinity of the distance between wk and the null space, and we've just seen that this distance is 1, so we get 0 equal, is greater or equal to 1, doesn't matter, this gives us a contradiction. So we've proven that assuming that this sequence is not bounded gives us a contradiction. So this sequence has to be bounded, and then we've seen that when this sequence is bounded, the f, the limit of the un minus t un, has to be in the range of I minus t. Okay, so we've proven that the null space has finite dimension, and we've proven that the range is closed. Now, the main idea of the proof I'm going to explain in this step 3 is the following. If we assume a condition that I'm going to call the split condition, that is that there exists a certain power, not necessarily 1, but a certain power and not such that x splits as the direct sum of the null space of I minus t raised to the power n naught plus the range of I minus t raised to the power n naught. Right, we may not have a null space range decomposition for n not equal 1, but let's say we have it for a high enough power. Then, okay, then the following happens. Then we remark that I minus t to the power n naught is of the form identity minus some operator s that depends on n naught, where s n naught is a compact operator on x. Right? You just expand that sum, and anything that is not the identity in the expansion of that sum would have at least one power of t, and because the space of compact operator is an ideal in the space of bounded linear operators, that is to say, if you multiply a compact operator by any bounded linear operator, you still get a compact operator. So everything else in the expansion of that sum is itself a compact operator. So step 1 tells us that the dimension of the null space of identity minus s naught has to be finite, and therefore the dimension of the null space of identity minus t to the power n naught has to be finite. And that gives us that the codimension of the range of identity minus t to the power n naught has to be finite. Yes, but identity minus t to the power n naught, the range of that is certainly included in the range of I minus t. So we get that the codimension of the range of I minus t has to be finite. Right, so this is really the key idea. The key idea is that we get the result as soon as we've proven the following split, which you could think of as being actually stronger than our result. So we're going to prove that there exists a certain power such that the space x splits into the null space of I minus t raised to a certain power plus the range of y minus t raised to a certain power, which is going to happen to be closed. Okay, so the way we're going to prove that is by proving first a stabilization of the null space and range of powers of I minus t. So let us define, say, Kn to be the null space of I minus t raised to the power n, and Mn to be the range of I minus t raised to the power n for all n. Okay, now remark that these things are nested, right? The range of I minus t to the power n plus 1 is certainly in the range of I minus t to the power n, and on the other hand, the kernel of I minus t to the n is included in the kernel of I minus t to the n plus 1 for all n. So now I'm going to introduce two conditions. The condition S1, which is that there exists an n naught, such that after that n naught, the kn's have stabilized, and S2, there exists an n naught, such that after that n naught, the mn do stabilize. And now step 4 of the proof is to show that if I have these two stabilization results, then I get the split condition. And we've seen in step 3 that the split condition includes the result. So that's what we need to prove next. We need to prove that Stabilization of the Kn and the Mn implies the split. And then the very last steps will be to prove S1 and S2. Okay, so let's pick N naught such that Kn is Kn naught and Mn is Mn naught for all n greater than N naught. Now I want to show that Kn naught intersected Mn naught is trivial, it's reduced to 0. So let's pick an x that is in Kn naught and in Mn naught. What can I say about that x? I can say that there exists a y such that x is identity minus t to the power n naught of y. And I can also say that 1 minus t to the power n naught of x is 0. So that gives me that I minus t to the power 2 n naught of y, that's right, is 0. And therefore y belongs to k2 n naught. But k2 n naught is kn naught. So y has to belong to kn naught, and therefore x has to be 0. Okay, so we've proven that the intersection of these two subspaces is trivial, and now we have to show that any element of x splits into one element of kn naught plus one element of mn naught. And you give me an x in x, I can pick a y in x such that 1 minus t to the n naught of x is equal to y minus t to the 2n naught of y, because, well, because mn naught is the same as m2n naught. Okay, but what does that tell me? That tells me that I minus t to the n naught of x minus I minus t to the n naught of y has to be 0, and therefore I can't write x as, well, I minus t n naught of y, which is in mn naught, plus x minus I minus t n naught of y, which is in k n naught, as we've just proven. Okay, so that proves the splitting S. So if we can prove that the sequence Kn stabilizes, that's S1, and the sequence Mn stabilizes, that's S2, then we have our result. So that's the conclusion of step 4. So now step 5, we're going to prove S1. Step 6, we're going to prove S2. Okay, step 5. Let's prove S1. Let's do that by contradiction. So assume S1 does not hold. Okay, now the first thing to remark is that identity minus t of kn plus 1 is always included in kn for all n, right? And that's because if I have an x in kn plus 1 and I look at identity minus t of x, and I apply identity minus t to the n of that, well, I get identity minus t to the n plus 1 of x, and so I get 0. Now, if S1 does not hold, we have that identity minus t of kn plus 1 has to be a proper closed subspace, closed because we've seen the range of I minus t is always closed, proper closed subspace of kn plus 1. That's for all n. Right? If not, S1 would hold at some point. You would have stabilization of this increasing sequence of subspaces. Now, okay, if that's the case, I can apply Ries's lemma. Well, you know, the version in Banach spaces, which is not with distance 1, but with, say, distance 1/2. And I would get that there exists a sequence, xn, in x, that satisfies the following property. Actually, it's in the unit sphere of x, and it's such that xn belongs to kn plus 1 for all n, and we have that the distance of I minus t xn to xn plus 1, so sorry, to kn plus 1, has to stay, say, above 1/2. Right, because the range of I minus t is a proper closed subspace of Kn plus 1. Okay, now this is the following consequence. Take two natural numbers, n and m, assume that n is greater than m. And then let's have a look at txn minus txm. I can rewrite that as txn minus xn plus xn minus xm plus xm minus txm. And the point of rewriting it this way is that I have now something here which is of the form minus I minus t applied to xn. And here I have an xn, which is in kn plus 1. Here I have an xm, which is in km plus 1, which is included in kn plus 1 because n is greater than m. And here I have something of the form I minus t xm, which is included in I minus t km plus 1, which is included in km, which is included in kn plus 1, again because n is greater than n. So really I have something of the form an element I minus t xn, and here something that belongs to kn plus 1. So this norm here has to be greater than the distance between I minus t xn and the subspace kn plus 1, and we've seen that this has to be greater than 1/2, and that's for every n and m as soon as n is greater than m. Therefore, txn, right, has no converging subsequence. And this contradicts compactness. Because xn is taken in the unit sphere by Riesz lemma, the unit sphere of our Banach space to start with, or the unit sphere of kn plus 1. But vectors of norm 1 in our Banach space to start with. Okay, so out of this bounded sequence we should be able to extract a converging subsequence for the norm, and we can't do that because this distance stays above 1/2. So this proves that S1 holds, and now we have one final step to prove that S2 holds. Okay, so for the final step, we assume that S2 does not hold, and we are going to run a similar argument as we did in step 5. So we have that mn plus 1 is a proper subspace of mn for all n, if S2 fails, and so we can apply Riesz lemma, or the weak version of Riesz lemma for every n, and we're going to get a sequence xn in the unit sphere of x that is such that xn is in mn for all n, and in the meantime the distance between xn and mn plus 1 stays above 1/2 for all n. Now, take an n and an m, natural numbers, assume that n is greater than m, and look at txn minus txm. Now, we can rewrite this as txm minus xn plus xn, and then minus txn. Okay, and what is the point of this? Well, we have xn here that is in mn. Okay, and n is greater than m, so this here would have to be at least in little m plus 1. And we have something here which is I minus t of xn, so it's even better, it belongs to mn plus 1, which certainly is included in mm plus 1. So this has to be greater than the distance between t of xm and capital M little m plus 1. Right, but what is that? This is equal to the distance of txm minus xm plus xm to m plus 1. And txm minus xm here, that belongs to m plus 1. So this distance is the same as the distance between xm and capital M, little m plus 1, which we know is greater than 1/2. And this contradicts again the compactness of T. Okay, and that concludes the proof. We've shown in step 6 that S2 holds, in step 5 that S1 holds, and then step 4 gave us that S1 plus S2 implies the splitting condition, and then the key step in step 3, we've shown that the splitting condition, splitting into the null space of a power of I minus t plus the range of the same power of I minus t was enough to guarantee finite codimension of the range of I minus t. Okay, so having proven the Fredholm alternative, we can now turn to the corollaries and start with corollary 13.4. So we're going to assume that the Banach space is separable, and under that extra assumption, we will show that the map lambda identity minus t for any non-zero lambda and any compact operator t is bijective if and only if it's injective, if and only if it is surjective. And this corollary will form the basis of the next corollary 13.5 and 13.6, building up to the fact that spectra of compact operators away from zero are only made of eigenvalues. Okay, so again, without loss of generality, we can assume that lambda is just 1. And what we need to prove is first that if the null space of identity minus t is trivial, then the range, which by the way is closed, has to be the full space. And secondly, if the range of I minus t is the whole space, then the null space has to be trivial. Okay, so let's prove one first. So we assume that the null space is trivial, and then recall from the proof of theorem 13.3, we've proven a little bit more as part of the proof of that theorem. We've proven that, so by the proof, we have that there exists an n naught such that x split as the null space of I minus t to the power n naught, and the range of I minus t to the power n naught. Now, as a consequence of that, we have the fact that this null space here is trivial. And the reason for that is because if you take an x that is in this null space, then you have that I minus t times I minus t to the n naught minus 1 of x has to be 0. But we know that the null space of I minus t is trivial, so by assumption, so we have that I minus t to the n naught minus 1 of x has to be 0, and you can repeat that argument, and inductively you get that I minus t of x is 0, and thus x is 0. So we have that the space x is really the range of I minus t to the power n naught. Now, what does that give me? That gives me that if I take an x, in x, there exists a y in x, such that x is I minus t to the power n naught of y. And in the meantime, there exists a z in x, such that I minus t of x is I minus t to the n naught of z. Now, if I put these two things together, what do I get? I get that I minus t n naught plus 1 of y has to be equal to I minus t n naught of z, and so I get that I minus t of I minus t to the n naught, say, of, no, actually just I minus t itself, of I minus t n naught of y minus I minus t n naught minus 1 of z has to be 0. But the null space of I minus t is trivial, therefore I get that I minus t n naught of y is I minus t n naught minus 1 of z. And so I can do that inductively, and remember that I minus t n naught was x. So I knew that my x was in the range of I minus t n naught, and now I get that my x is in the range of I minus t to the n naught minus 1. And I can repeat this reasoning and inductively get that x is in the range of I minus t, and my x was an arbitrary element in x, so we've proven that the range of I minus t is the entire space. Now that proves 1. Let's have a look at 2. So now we assume that the range is the whole space, and we need to deduce from that that the null space of identity minus t has to be trivial. So let's assume that the range of I minus t is the whole space. Okay, so I want to go from that fact to the fact that the null space of identity minus t star, the adjoint of t, is trivial, and then go from that to identity minus t having trivial kernel. So let's see how that works. I take an element x star in the dual, and I actually assume that it is in the null space of identity minus t star. We know that t star stays compact. So now what have we got? We've got that if I take an x in x, there's going to exist a y in x such that x is I minus t of y, because the range of I minus t is the entire space. So when I apply x to x star, I'm really applying x star to I minus t of y, and so moving the adjoint to the other side, I get y applied to I minus t star of x star. But I minus t star of x star is 0 because x star is in the null space of I minus t star. So what have I proven here? I've proven here that any x star in the null space of I minus t star is 0 when tested against an arbitrary element x in x. So that is really giving me that x star is 0, and therefore this null space has to be trivial. Okay, but now I can apply 1 in x star using that t star is also compact, and I get that the range of the I minus t star has to be the entire dual. Now take an x in the null space of I minus t, and we're going to somehow reverse the first part of that argument, and take an x star in capital X star. There exists a y star in x star such that x star is I minus t star of y star, because the range of I minus t star is the entire dual. And when I look at x, apply to x star, then I'm really applying I minus t star of y star, and now you use property of adjoint, you get I minus tx applied to y, and I minus tx has to be 0 because x is in the null space. So that means that x itself has to be 0 because I've tested it on any x star and capital X star, so in particular I could take a non-link functional, and I get 0. So x equals 0, and the null space is trivial. And that concludes the proof of corollary 13.4, injective equivalent to surjective equivalent to bijective for operators of the form lambda identity minus t, where lambda is non-zero and t is compact. Okay, so let's do this by contradiction. Let's give ourselves an epsilon and assume that there exists an entire sequence of lambdas that are in the spectrum and that are such that their length is at least b0 epsilon, and they're distinct. So lambda n is equal to lambda m if and only if n is equal to n. Okay, now we know that lambda n being in the spectrum of T implies, by corollary 13.4, that the null space of lambda n identity minus T is non-zero. So that is to say, there exists, it's an eigenvalue and there exists an eigenvector. So there exists a sequence xn in the unit sphere such that lambda n xn is equal to txn for all n in n. Okay, so I claim that these xn are linearly independent. And the way to see that is by induction. Yeah. Okay, it's very clear for just one element, but if we assume that the first, say, n plus 1 of them are linearly independent, and that the next one is a linear combination of the first n. And xn plus 1 equals sum of alpha j xj, j equals 0 to n for some alpha j's in Rn plus 1. Well, okay, then what happens? Then lambda n plus 1, xn plus 1 is going to be t of xn plus 1, right? And because xn plus 1 is an eigenvector, and so this is going to be the sum of alpha j t of xj's, j equals 0 to n, and the t of xj's are lambda j's xj's. So alpha j lambda j xj, j equals 0 to n. Okay, but so that is to say that lambda n plus 1 alpha j xj, this sum, j equals 0 to n, is equal to this sum, j equals 0 to n, of lambda j alpha j xj, and so by linear independence of the xj up to n, I have that lambda n plus 1 alpha j is equal to lambda j alpha j for all j. Right, and that's a contradiction because lambda n plus 1 cannot be equal to lambda j for any j. Okay, so I have my xj's linearly independent, and I'm going to define yn to be their span, the span of the first n plus 1 of them. And then I have that yn is strictly included in yn plus 1, right? Because in yn plus 1, I add a vector which is linearly independent from any element in yn. Okay, but then we can apply Rees lemma once again. Okay, and that's going to give us a sequence yn in the unit sphere that is such that yn belongs to capital Yn for all n, but the distance of yn to capital Yn minus 1 is greater than 1/2 for all n in n. Okay, now what can I do with that sequence? I can say, because yn is in capital Yn, for every n, there exists a sequence alpha jn, j equals 0 to n in Rn plus 1, such that yn is the sum of alpha jn xj, j equals 0 to n. And therefore, for every n and m in n, let's say n greater than m, what can I say about t of yn minus t of ym? It is going to be the sum j equals 0 to n of alpha jn lambda jxj minus the sum j equals 0 to m of alpha jm lambda jxj. Okay, and now I can rewrite that as yn times lambda n minus what? Minus the sum j equals 0 to n minus 1 of the alpha jn of lambda j minus lambda n xj, and then minus the sum from j equals 0 to m of alpha jm lambda j xj. But the point is, this entire thing here is certainly in capital yn minus 1, and my lambda n cannot be 0 because it is greater than epsilon. So this is equal to yn minus zn for some zn in yn minus 1. Okay, maybe times lambda n. And lambda n is a non-zero number because it's greater than epsilon. So this entire thing is greater than epsilon times the distance between yn and capital Yn minus 1, which is at least 2. So this has to be greater than epsilon over 2. And this contradicts, once again, the compactness of T, because I can't extract a converging subsequence from T of Yn despite T of Yn being bounded. Now that concludes the proof of corollary 13.5. So away from a ball of radius epsilon around 0, the spectrum has to be finite. Now to get corollary 13.6, let us make an additional remark on the proof of corollary 13.5, and that is that if you have a whole sequence lambda n of eigenvalues of T that are non-zero, then by the reasoning above you get that T of Yn divided by lambda n minus T of Ym divided by lambda m has to stay greater. So if I divide by lambda n, I don't need to bring the lambda n at the front like I did here and estimate it by epsilon. I just get that this thing is greater than 1/2 for any n and m. Now, if lambda n converges to something, to lambda, and lambda is non-zero, then by compactness, I can pick y and k and lambda and k subsequences such that T of y and k converges, right? That's by compactness. But then if my T of y and k converges and my lambda and k converges, then I should get that T of yn k divided by lambda and k minus T of ymk divided by lambda and k would have to go to 0 as k goes to infinity. And this contradicts the fact that it has to stay above 1/2. So if by lambda n, if I have an entire sequence of lambda n, let alone if I have more than a sequence, if I have uncountably many, I can pick a sequence, and if that converges to anything but 0, then I get a contradiction. Putting all of this together, we get corollary 13.6. So at least in separable Banach spaces, we have the same results that we did get in Hilbert spaces, namely the fact that for compact operators outside of 0, every element of the spectrum has to be an eigenvalue, and that the set of eigenvalue is either a finite set, or if it's a sequence, that sequence tends to 0. Now, the way you get that is, well, with the proof of corollary 13.5, you get the fact that it has to be a sequence or a finite set, and that if it's a sequence, the only passable limit point is 0. And then from corollary 13.4, you get the fact that if you are an element of the spectrum, then you're not in the resolvent set, and 2 cannot hold, therefore you have to have an eigenvector, therefore you have to be an eigenvalue. And notice that this is just in our use of duality in corollary 13.4 that we picked up the assumption of separability on the Banach space in order to have the sequential version of the Banach-Cataloglu theorem.